In this section, we'll be talking about the fundamental theorem of calculus. Has a rather auspicious ring to it, doesn't it? And it's a rather auspicious theorem as well. It's from one standpoint, from the manipulation standpoint, it's kind of the marriage of the idea of integral function and the idea of a definite integral. We bring those two ideas together into one idea. But from a more conceptual standpoint, it is the culmination of the inverse idea between differential calculus and integral calculus. And that's not too surprising, actually, because if you think about the essence of those two ideas, the differential calculus and the integral calculus, then you can see this inverse relationship. And it's kind of interesting. Let me just show it to you here as a point of interest. But the differential idea has to do with the slope of the tangent line at a point, and you know that slope is this rise over run idea, but it's a delta y over delta x notion. And that's that's the sort of the essence of the differential idea or derivative idea. Now the integral idea has much to do with the notion of area, and when we calculated areas, we were taking the areas of little rectangles and adding them together. And when we calculate those little areas can be thought of as, well, let's see, a horizontal distance times a vertical distance, you see. So it's kind of like a delta x times delta y, you see, to calculate those areas. And notice the inverse idea here involved in these two calculations. Well, that's just fundamentally or conceptually the way that differential calculus and integral calculus are inverses of one another. Now, let's get to the idea of the fundamental theorem of calculus being the marriage of this integral idea, the integral function, and finding an integral on a definite interval. And recall that when we calculated the integral function, we calculated it like this, where the integral of x squared plus 3 dx is x cubed over 3 plus 3x plus a constant. Now, and we studied all about that kind of thing. Then we turned our attention to the integral within an interval, and we made the calculation according to the limit of a sum, and the calculation went something like this. The discussion went like this. Now notice I'm using the same function that we had over here, but we're finding the integral between -1 and 2. And the geometric interpretation of this was the area under the curve of this graph within the interval -1 to 2. And between that graph and the x-axis and within that interval. Okay, so we make the calculation as the limit as n approaches infinity of the sum as I runs from 1 to n of f of c subscript I times the delta x. And we have a little calculation for all of these things. The delta x is found as b minus a over n. And the b is the 2 and the -1 is a, so it's 2 minus -1 over n. 3 over n then would be the delta x amount, the length of each of those, or the width, I should say, of each of those rectangles. And then the c sub I is it's a horizontal distance that falls within the ith interval, and that's a good way to think about it. And we can choose any point within the ith interval to use for this value. And we could choose the first point, the last point, the midpoint, any point in between if we want to. And one easy way to calculate or to identify the c sub I value is to start with a, the left endpoint of our interval, and then put a counting mechanism on our delta x. And that's all this symbolism tells us to do. And then we make the calculation like this, true to our particular information on this integral, and then we pop that information into the limit idea. So it's the limit as n approaches infinity of the sum of f of, and we use this, and then times the delta x from up here is 3 over n. And then we go through that process of evaluating and expanding, manipulating, and so forth, and we'll find this integral to be 12. Well, you'll be delighted to know that we need not go through this process for a little while. We're going to marry the two ideas of the integral function with this idea of a definite integral. And that is the fundamental theorem of calculus, and it is very simply this, that the integral, the definite integral now, from a to b of f of x dx is big F of b minus big F of a. Now big F is the integral function of this f. Okay, so it's the integral function evaluated at b minus the integral function evaluated at a. And that's all there is to it. Now we use a particular notation, and rather than this kind of notation every time. It's a little bit easier from a manipulation standpoint to just say big F of x and then use this notation as for the lower and upper limits of our integral. And it looks like this if we're actually performing the operations. And I'm finding this integral that we found earlier. Remember, it was 12. And so here's what we're looking for. And we make the calculation very quickly like this. Just think about the integral of that function. The function that is the integral of this function, you see. Calculate that right quick. Well, let's see. It's x cubed over 3 plus 3x. And then there would be a plus c on there, and I'll tell you why we don't need to use the c in just a minute. But so we leave out the c, and we have this important information. And then the integral is from -1 to 2, so we put the -1 and the 2 over here. So we have all of our information necessary for the calculation. Now we want to compute the f of b minus f of a, and it's easily computed from here. So the f of b, that's f of 2. That's big F now of 2. So we pop a 2 in place of these x's, and it looks like this. And then minus f of -1. So put a -1 in place of these two, and then it's a manipulation situation. And resolving this becomes 8/3, and then this is 6, and -1 cubed is -1, so this is -1/3, then minus 3. All right, then this 8/3 is 2 2/3, and the 6, the minus the -1/3 is 1/3 minus -3 plus 3. And collecting here, we find this to be 12. So it's pretty easy to see that this is a much simpler process than going through that limit of the sum idea. And in fact, you might try going through that limit of sum routine to find a definite integral a little bit later when we get to some of the more complicated problems. It's quite a distinct difference between those two processes. Well, I mentioned that I would tell you why the c is not needed. You know, if we're going to put a c in here, then we would have a plus c involved in this parenthesis and a plus c involved in this parenthesis. And notice we're subtracting all the items in this parenthesis, and so the c's would just automatically go out every time, so there's no sense in writing the c each time. Well, let's go through the process with another problem. This one says we want the integral from 0 to 2 of 2 minus t times the square root of t dt. And we want to rewrite this in a simpler form, in a form where we can easily find the integral function. And so we'll do that by thinking of this t as t to the 1/2. So it's t to the 1/2 times 2 is 2t to the 1/2, and then t to the 1/2 times minus t is minus t to the 3/2. And now we're ready to go with using the fundamental theorem of calculus. Take the integral function of this, and we have 2t to the 3/2 over 3/2 minus t to the 5/2, I'm adding one here, t to the 5/2 over 5/2. And now we use this little notation over here to define the limits of our integration, and it's 0 to 2. And so we find, well, let's clean this up first. We're going to do the f of b minus f of a in a moment, but let's clean this up a little bit. The 3/2 in the denominator becomes 2/3. It's 2/3 of 2, that's 4/3. t to the 3/2, and then this becomes flip over 2/5 t to the 5/2. And now we want big F of B minus big F of A. So f of B means f of 2, so pop a 2 in place of these t's and rewrite, and then put a 0 in place of these t's and rewrite, and we have this. Now, fortunately, when a 0 is involved, and then a lot of the terms will simply go out. This whole expression will go out of the problem, so we're evaluating this. And it's just a matter of manipulation. 2 to the 3/2, and I've written it up here. It becomes 2 to the square root of 2, and 2 to the 5/2 is 4 to the square root of 2. So we have this 4/3 times 2 root 2 minus 2/5 times 4 root 2. And then again, cleaning up, 4 times 2 root 2 is 8 root 2 all over 3. And here, 2 times 4 root 2 is 8 root 2 all over 5. Now, at this point, you could pop the information into a calculator and get a pretty good approximation of the value. But, you know, when you look at or try to refer to answers in the back of the text, sometimes the answers are written in an approximated form, sometimes in an exact form. And we have to understand the difference between the two and be able to manipulate toward any form that we may see or want to compare to. So here, if we're looking for an exact form, then we would look probably at finding a common denominator, which is 15, multiply here by 5 over 5 and we get this, multiply here by 3 over 3 and we get this. Common denominator means we collect the numerators. 40 root 2 minus 24 root 2 is 16 root 2, and all of that is over 15. So here's the exact form, and again, we could pop this into the calculator and get a pretty good approximation very quickly. Also, I want to invite you, now I'm only showing one example here. I invite you to look at the examples that are in your textbook to get a feeling for this process. The process can go very rapidly, and you ought to be very comfortable with the idea. And we can also make the calculation, kind of verify what we're doing right here by using the graphing calculator. Calculating a finite integral is incredibly easy on the calculators. And in fact, we can approach the situation from two different points of view. We can use an algebraic approach on the calculator or a geometric approach. That is, we could use the graph. Well, let's use the algebraic approach first, and then I'll show you the graphing idea later. I press the Math button on the TI-83, and I'm cursoring down to item number 9. Press Enter, and now we need the information about our integration situation. We want the function first of all, and then the variable of integration, and then the limits. So let's see, the function is, I'm opening another parenthesis here, 2 minus x, close parenthesis, and we want to multiply this times the square root of x. And now, it's important here to close this parenthesis. You know, with the TI-83, when the square root symbol is used, the opening parenthesis is automatic. You need to close it. If you don't close it, you get a little error message, and you have to have as many closed parentheses as you have opens, and so you'll know right away if you make that kind of mistake. I make it all the time, so I know. At any rate, let's see, the variable of integration is x, and then another comma, and lower limit 0, comma, upper limit 2, close parenthesis, and if we've done everything correctly with closing those parentheses, here we have the finite integral. It's thinking 1.508 and so forth. Now, we didn't make the calculation like this on the board a few moments ago. The calculation was made as a fraction. Let's go ahead and verify that it's the same number that we have here. And we can do that. Well, we can do that like this. We had on the board 16 times the square root of 2 and divided by 15. And oh, sure enough, it's accurate to, oh, I don't know, 6 or 8 decimal places anyway. Okay, the other way to approach the situation is to plot the graph first of all. I've already entered the function here, and here's the graph. Now I am using some rather creative window settings. I'm trying to make the window rather friendly for tracing purposes or for moving around the window. I'm actually not exactly tracing, but it's kind of like tracing what I'm going to do. in just a moment. Now to calculate this, this integral, I want the calculation menu. That's the second function on trace, so I'm pressing second and trace. And now I'll go down to item number 7, the integral of f of x dx. And it's asking me for the lower limit, and the prompt is for me to cursor over to it. So this is kind of like tracing, isn't it? And I'm going over to the point of x being 0. Oops, passed it. Here it is. Okay, x is 0. Press enter, and now the upper limit, going over to the right. Now you see why it's kind of important to have friendly settings here, because if we didn't have friendly settings, we might not be able to land exactly on 0 or exactly on 2 here. Pressing enter. Notice the calculator even shades the region for us and gives the integral. Well, on the TI-86, it's a very similar kind of procedure. And let me slide the 86 in here right quick. Turn the calculator on. And it's the same idea. We can use either approach we'd like. Let's look at the graphing approach first. I have already entered the function here, and I'm using standard settings, and the graph looks like this. Now with standard settings I get a little bit broader view of the graph like this, but we can make the calculation right here on a graph that looks like this, or we could change the graph a little bit. It really doesn't make too much difference. If I press more and enter the math menu, then the item I would like is this item, the integral of f of x. And once again, I'm asked for information about lower and upper limit. I've entered for lower limit, and I'm sliding over here to x equals 2 for the upper limit. And the calculation is being made. Now, actually using a broader view like this, it's kind of easier, a little bit easier for us to trace over from one limit to the other. If we have a broader view, we have to trace a lot more pixels, so there are some advantages here to take a broader view. Anyway, that part of it is strictly up to you. Let's leave this area and go to the blank screen and look at it sort of algebraically. Now we're selecting, we want the calc menu. It's the second function on the division sign, so second and then divide will be the calc menu, or the calculation menu. And we want a definite integral, so that's F5 here. And same idea as we had before. We'll enter the function the same way. And this is very predictable at this point. Square root of x. Now you'll notice that on the TI-86 there's no automatic opening of parenthesis here, so we don't have to close a parenthesis at this point. It's kind of a little bit of a different process here on the TI-86. Comma, the variable of integration, comma, lower limit, comma, upper limit, close parenthesis, enter. And here's the integral as expected. In a previous segment, actually a previous chapter, we talked about the mean value theorem. And there is a mean value theorem for integrals. Let me refresh your memory about the mean value theorem that we talked about earlier. The formal definition looks kind of like this. If f is a continuous function on an interval a to b, there exists a point c in the interval a to b such that f prime of c, f prime of that point that's in the interval, is f of b minus f of a over b minus a. Now, this is just the idea of slope, and it's the slope calculated using the endpoints of the interval. You see, this is like a y2 minus y1 over x2 minus x1. All right, so, and the geometric interpretation is this, that if we take the slope, we calculate the slope involving the endpoints of the interval. That slope, you see, can be found at some point on the interval. That is, f of c is right here, and the slope at that point, the slope of the tangent line at that point, is the same as the slope calculated using the endpoints. Well, perhaps a more informal way to say that is that there is a point within an interval that gives the average rate of change for the entire interval. You see, and that's all this is. It is a rate of change at a point, and this is the average rate of change for the entire interval. That's all there is to that. Now, for integration, for integrals, it's a very similar kind of idea. But here we're talking about areas under curves, and so if we're talking about the interval a to b, and we know that the integral would be the area within these bounds. All right, and we know that. Now, gee, how do we calculate that? You know, we have on this rate of change idea, we have a rate of change at the beginning of the interval. We have varying rates of change all over the interval. We have a rate of change at the end of the interval, but gee, we can actually find a c so that we have an average rate of change with it for the entire interval. Well, here it's the idea that for some there is a rectangle like this one, which is an inscribed rectangle, and clearly the area of this inscribed rectangle is smaller than the area under the curve. And there is a circumscribed rectangle, and it's roughly at this end point. I tried to draw it at the end point. It doesn't have to be at the end point, but it's kind of easy to think about if it is. You see, so we have a circumscribed rectangle, and the area of this rectangle is more than the area under the curve, you see, because it contains this area as well. But there exists some point, you see, along this interval such that, and let's say that it's, I don't know, maybe right here for C, that for that spot, for this f of C, there is a rectangle that is exactly the same as, the area of this rectangle is exactly the same as the area under the curve. Okay, that brings us to the mean value theorem for integrals. This is what it's all about. If f is a continuous function on the interval a to b, then there exists a c, a point c in that interval, such that the integral of the function within that interval, you see the area under the curve, is simply f of c times b minus a. Now f of c times b minus a, come back over here and let me show you what that's all about. F of c, you see, is this distance. That's f of c. Multiply times b minus a, and you're multiplying by the length of this rectangle. So it's length times width. That's all there is to it. So you're just multiplying the dimensions of the rectangle to get our integral idea. Now, the f of c is called the average value of the function on that interval. So average value. And you might think, gee, if there's this average value, if it exists, and notice that it only tells us that the average value exists. It doesn't tell us how to find it. But if the average value can be found, you may think, gee, this is a great way to calculate integral, because after all we have to do is take that average value and multiply by the length of the interval, and we have the integral. Well, unfortunately, life isn't that nice. We don't have a very neat way to calculate average value unless we have the integral. It's not like we find average value and then we calculate integral. It's that we find the integral and then we calculate average value. Now, to understand how the average value is calculated, we can solve this equation for f of c. Just multiply on both sides by 1 over b minus a, and f of c is 1 over b minus a times the integral of the function within that interval. Now let's go through the calculation of average value using a specific function. Suppose we want to find the average value of this function on the interval from 1 to 4. And we'll proceed like this. Average value is, according to our formula down there, 1 over b minus a times the integral from a to b of f of x dx. And the b minus a part, let's see, we're running from 1 to 4, so it's 4 minus 1, you see, and then the integral from 1 to 4 of our function. And now we want to use the fundamental theorem of calculus to make this calculation. So the big F, the integral function here of 3x squared minus 2x is 3 times x cubed over 3 minus 2 times x squared over 2. Now we can simplify here. The 3's go out, the 2's go out. How convenient, we have x cubed minus x squared. And the interval again is 1 to 4. So we take big F of 4 minus big F of 1. So the big F of 4 would be replace these x's with 4's, and then subtract, replace the x's with 1's, and then evaluate, and evaluating here we get 16. So the average value of the function is 16. Now, the graphical interpretation of the 16 is this, that here is the graph of the function along the interval from 1 to 4. Now notice at the beginning of the interval we have the point 1, 1. At the beginning at 1, f of 1 is 1. And at the end of the interval, f of 4 is 40. It's a lot further up here than I'm showing, but this is just a pretty good idea of what's going on. Now, average value of the function means that since by the intermediate value theorem, within this interval, f of x is going to take on every value between 1 and 40. And it's going to take on that very special value that is 16. That is the average value of the function throughout the interval. So at some point, a point maybe right in here, let's say, we have f of that point is 16. So this then is average value. And it is 16 for this problem. Now, it is the average value itself that is often important to us in certain specific problems, but suppose we wanted to know, and it's pretty easy to figure out, the value along the interval such that f of that value is 16. You see, so it may occur that we would like to know what value along here will produce this average value of the function. And we can do that like this. It's a pretty easy calculation. It's just an algebra calculation. But to find the x such that f of x is 16, f of x is this expression, set it equal to the 16 and solve for x. You see, kick the 16 to this side, factor, and now we want the zeros of the factors. So the 0 for this factor would be 8/3. The 0 for this factor is -2. Throw this one out because -2 doesn't appear within the interval we're talking about. This 8/3 is 2 2/3. So this value right here is 2 2/3, such that f of the 2 2/3 will give the 16. Before we leave this topic, I want to clear up a couple of things. I may have led you astray when I was talking about the last problem, that particular problem where f of one endpoint happened to be 1 and f of the other endpoint happened to be 40. And it so happened that 16 is between 1 and 40. It doesn't necessarily follow from this intermediate value theorem for integrals that the value we're looking for is in between f of a or f of b. Look at this situation. Now, graphically, we can see it much easier than we can algebraically. But f of a is this, f of b is that, and clearly, if we want a value c such that f of c is the average value of the function. Now notice the function values go way up and then come way back down through this interval. And so the average value of the function will be somewhere in this neighborhood, not necessarily between f of a and f of b, you see. So I don't want to leave that impression. It just kind of so happened with that other one, and I use the idea of the intermediate value theorem. I just kind of threw that in. It doesn't really have a direct correlation with this idea of intermediate value theorem. Okay, another point that I want to make is that the value, the average value is not unique within the interval. And it happened to be unique with our other function, our previous function, because it was continually increasing throughout the interval. But here we have a function where, let's say the average value of the function is, roughly maybe, let's say here, that this is the average value of the function. And it's an average value if it turns out that, you see, we can form a rectangle here such that f of that value, f of some c here, f of c is the average value, f of c times b minus a is the same as the area under the curve originally. So if we can find that value, then we have an average value, but it is an average value and not the average value, because after all, there's another spot like that over here, you see, for this particular function. So the value, the average value is not unique. There may be a c here. We might call this c subscript 1, and this one as c subscript 2. You see, and f of c sub 1, f of c sub 2, both give the average value for this particular function. So it's not a unique value is what I'm saying. I'm about to show you a problem from your text that really grabbed my attention, so prepare to be impressed. It's a problem that has to do with the average speed of sound. And when I saw the problem and it says average speed of sound, it occurred to me, I said, gee, I thought the speed of sound was constant. You know, this is kind of the laws of physics, and these things don't change just randomly. Well, it kind of makes sense that sound travels at a different rate at different altitudes. Now that's one intriguing thing about that. Now that part of it kind of makes sense to me, because after all, the air is denser the closer to the earth that you get, and it's thinner up above, and sound depends upon this density of air, I'm thinking, and maybe even humidity and such things as that. Okay, fine. But I also found within the problem that as you go higher and higher, sound travels a bit slower for a while, and then you go a little higher than that, and sound tends to go a little faster. And take a look at the graph of it in your book. It's just the most amazing thing you've ever seen. But what we want to do here is make the calculation of the average speed of sound within a certain interval of altitude, an altitude range, and it's from 0 to 80 meters. Now, the speed of sound can be modeled within that interval 0 to 80 meters altitude like this. Now this is a piecewise function, and when x, the altitude, is between 0 and 11.5 meters, then we can model the speed of sound with this linear equation. And between when the altitude is 11.5 meters to 22 meters, it's 295 meters per second, and so on, and you can see the various calculations. And when I first saw this, I said, well, gee, okay, fine, we make a different calculation, and the idea of the change in the speed of sound is just not a linear idea completely. Okay, I kind of understand that. But what really threw me with this problem was the idea that, and it's not part of the calculations that we're doing here, it's just an intriguing aspect of the problem. It is that as you get above a certain height, that sound starts to go faster. You know, the speed of sound is faster as you go, and then it begins to drop again. Well, anyway, that's a really fascinating thing to me. But we can make the calculation of average speed within these height distances, these heights from 0 to 80 like this. We'll take, here's our function within this interval, and we'll calculate the integral within that interval. And then we'll calculate the integral within this interval, and so on. And then we will add those integrals within those various intervals, and that sum will be the total speed, if you will, within the interval from 0 to 80 meters. And then all we need to do is divide by, well, think about it. We divide by 1 over b minus, we multiply by 1 over b minus a, which means that we divide by b minus a. And the b and the a here are 80 and 0 respectively, so we're dividing by 80. Here's what the calculation looks like. We take the integral from 0 to 11.5, and that's modeled by this part of the function, dx, and it turns out to be 3657. And an interpretation of 3657, this is the area under the curve within the interval from 0 to 11.5. It's kind of like the total speed within that interval. Which is a kind of an interesting thing because it's like we're accumulating speed here. We have a numerical value which is the accumulation of speed within an interval. Interesting notion, isn't it? And then here, the accumulated speed in the interval 11.5 to 22 turns out to be 3097.5, and so on for all of the other little intervals and the various sort of sub-functions that we have, the piecewise function that we have. And then what we have totally for all of these integrals, we have the integral from 0 to 80 of that speed function is the total of all of these values, the total of these integrals is 24,640. Now the average speed, you see the average value of this function is 1 over b minus a times this. So it is average speed of sound, then is 1 over 80 times this, which is, and this part was the 24,640 divided by 80, and we find the average speed within that interval to be 308 meters per second. Now if you look up the speed of sound in various textbooks, physics books and a dictionary and so forth, you don't find 308. They're not going to give you the average speed of sound from, within a certain altitude range. That's not the idea. They're going to give you a representative speed of sound probably near sea level. And that representative speed of sound near sea level is given normally as 330 meters per second or something in that neighborhood, or 740 miles per hour. And these are pretty much equivalent to one another. But a really fascinating problem. There's also some information about the airplane that first flew the speed of sound. If it had flown at a different altitude, it would have not reached the speed of sound at the rate at which it was traveling. Interesting idea. Suppose we have an interval like this, and along that interval we want to take various integrals. We want the area under the curve at 1. That is, we want this area. And then we want to calculate the area under the curve within the interval 0 to 2. And then from 0 to 3, and then from 0 to 4. You see, these are just various areas that we're calculating. Well, one way to do it would be to find the integral from 0 to 1 of f of x dx, and then for the next value we take the integral from 0 to 2 f of x dx, and then the integral from 0 to 3 f of x dx, and then the integral from 0 to 4, and so on. Well, another way to do it, maybe, rather than making these separate calculations, is to make the upper bound of the interval variable. Now, what would that do to the calculation? Now, think about it a little bit. Here's what happens. What we've been doing is this. We have a definite interval, a to b, where a and b are constants, f of x dx. All right, we know what that looks like. That's just a number. But when we're talking about the definite integral as a function of x, or putting a variable into the situation, then here's what's happening. We have the integral from a to a variable x of a function, and it's a function of any variable, f of t, f of c, f of d, whatever, d times d that variable, f of t dt, you see, for example. Then it turns out that this is an antiderivative function in terms of x. In terms of x. Why is that? Well, because this is big F of x minus big F of a, remember. And so what we're talking about here is a function in terms of x. Let me show it to you with an example. Suppose we're talking about the definite integral 4 to x being a variable now, and we're talking about the square root of t dt. Well, this is t to the 1/2 t dt. Well, this is t to the 1/2 dt, all right, and the antiderivative of t to the 1/2 is t to the 3/2 over 3/2, and we're evaluating 4 to x over here. Now, cleaning this up a little bit, this is 2/3 t to the 3/2. Now we go to that f of, big F, of upper limit minus big F of lower limit. So we have, here's big F. Big F in terms of x means replace the t with an x. And then big F of 4 means replace the t with a 4. So we have this. And what we have here then is an antiderivative function in terms of x. So this is f of x, you see. All right, rather interesting twist, kind of a juxtaposition in our use of variables here, and maybe something that's rather unexpected. Well, here's something else that's intriguing about this. Here's the f of x that we just calculated, the big F of x now, antiderivative function of x. Suppose we take its derivative. You know, when we talked about antiderivative functions earlier, it turned out that, gee, we could check to see if they were truly antiderivative functions if we could take their derivative and get the function that we started with. You see, we start out with an f of x, we calculate a big F of x, and then the f prime of x, the big F prime of x, gives us the f of x back. Rather nice little inverse relationship there. Well, that's great. But in this circumstance, look at what happens. We have f prime of x is the derivative of this, okay, the derivative of this in terms of x. And its derivative, well, let's see, it's 2/3 times the exponent 3/2 times x to an exponent that's 1 less than this. 3/2 minus 2/2 is 1/2. So this is, these go out, cancellations all around here. X to the 1/2 is the square root of x. So what we have here is the function f in terms of x, f of x. Now f started out as a function of t, f of t. But the f prime of x is f of x. So basically we have here is that the derivative of this integral from 4 to x of the square root of t dt turns out to be the square root of x, which is f of x. We're starting out with an f of t right here, and we end up, when we go through this process kind of both ways, we end up with f of x. Now that is the essence of the second fundamental theorem of calculus. Calculus is so neat that it has two fundamental theorems. And the second fundamental theorem of calculus is that the derivative of this definite integral, but with a variable at this upper limit of f of t, and this t could be any variable that we'd like to choose, it is fine, but the derivative of this integral turns out to be f of x, not f of t. Rather somewhat surprising, perhaps. So if we started out with the integral from 1 to x of this function dt, and we can call this the antiderivative function of x. We know it's an antiderivative function of x because of the x that's right here. But when we take its derivative, we have this function in terms of x, not in terms of t. So we have this coming back at us. Some rather interesting things can happen when our upper bound or lower bound or both differ from just x. For example, here, if we're integrating from 2 to x squared of 1 over t squared dt, we know that this can be expressed as thought of as a function of x, but gee whiz, what is it? What is its value? And we're going to go on within this problem to actually find the derivative of that big F of x and see what that is. Now we know that generally if this were an x, we know that big F prime of x would be little f of x, or it would be 1 over x squared. But now let's just examine what happens in this circumstance. Now we'll go through the process of finding the antiderivative function, and we're thinking of 1 over t squared as t to the negative 2. And now the antiderivative function here would be t to the negative 1. You see, increase this by 1, and then divide by this exponent. It's negative 1. Clean this up, and this is negative 1 over t. Now we want to take big F of upper bound minus big F of lower bound. So big F of x squared means replace t with x squared. And big F of 2 means replace the t with 2. So we have this. And then this becomes plus 1/2. So here's what big F of x turns out to be, and I've repeated it up here. And let's go through the process of examining what big F prime of x would be, the derivative of this. Let's see what turns out. Well, we're taking the derivative of this expression, and I'm just writing this as x to the negative 2 for convenience. And let's see, we would have negative 2 times negative 1, that's 2, and reduce this by 1, so we have x to the negative 3. So 2x to the negative 3, or 2 over x cubed. Now this is a rather unexpected outcome, because we started out with f of t. Now let me put it right next to this. F of t was the 1 over t squared. And when we went through the process, sort of back and forth, with the integral and the derivative, we would have expected perhaps to get something like, maybe 1 over x squared squared, because that upper bound was x squared. So if we replace t with x squared, x squared squared would be x to the 4th. This isn't 1 over x to the 4th. You see, what is this? Well, let's examine it like this. Consider our original situation, which is this. And we're thinking, would it be that f prime of x would be f of x squared, f of this upper limit? And if it is, then let's see, in this situation we would replace the t with the x squared, so we'd have 1 over x squared squared, or 1 over x to the 4th. No, that's not it, as we mentioned earlier. But look what happens if we take the derivative of this and multiply it into this situation as a factor. The derivative of the x squared is 2x. Pop in that 2x. Oh, happy day, we have a cancellation of the x's, and we have 2 over the x cubed that we had here. So it's kind of like using the chain rule in this situation, and it is indeed using the chain rule in this situation. So here's our f of x is the integral of 2 to x squared of 1 over t squared dt. And I'm just showing you another view of the same thing here, using this substitution of a u into the situation to show the whole process. If we let u stand in for x squared, then this becomes the integral from 2 to u. And then when we talk about a big F function, you see, then then the F prime business, it's F prime of x is the derivative of f in terms of u. You see, it's this in terms of u, so it's 1 over u squared. And then we multiply times the du dx, the derivative of u with respect to x, and therefore we have f in terms of u times the u prime. And for this problem, it turns out to be 1 over u squared times, now the u prime, remember u was x squared, so the derivative of u would be 2x, and the u is the x squared, so this is x squared squared, or 2 over x cubed. So that's the way the process works. But you know, this is, it's kind of like when you first learn the chain rule, it seems so complicated, and all of this symbolism and so forth seems so confusing. But really, it's a lot less confusing than this. Here's how it actually works in practice. If we have f of x is the integral from, let's say, 0 to 3x of this function of t and dt, and we want f prime of x. Well, all we do is write down this function in terms of the upper limit here. So replace t with 3x, and we have this. And then multiply that. You see, all this is f of, this is f of t. We want f of 3x, f of upper limit. Fine. All right, then multiply times the derivative of the upper limit, and that's the 3 here. So, and that's as fast as it goes. And so clean this up a little bit and multiply times 3, and that's our answer, and it happens very, very quickly.